So let's get started with the backside of the photoelectric effect worksheet. Okay, in a photoelectric effect, a metal absorbs photons with the energy that's 6.0 times 10 to the negative 19. We have to realize that this is the energy per photon of light. That photon is a packet of light, and we know that its energy, okay, is equal to Planck's constant times the frequency. So the energy is proportionate to the frequency, high energy. Now, so this is the energy per photon of light, and this equation is per photon. Now, the maximum kinetic energy of the ejected electron. So we've got a packet of light with a certain frequency, strikes a metal, and then what we have is we have an ejected electron because that photon, okay, had enough energy that exceeded the threshold, so electrons were ejected with a certain kinetic energy. And so what we know is, this is important, that the energy of the photon, and I'll just say photon, is equal to two other energies. Well, the other energy, of course, is the energy, and I guess I should have had that in blue, but hey, I'm tall. Okay, the other energy is the energy needed to remove the electron. So this is the binding energy, and then plus the energy of the speed of the electron. This is the kinetic energy. So the total energy of the photon, if it exceeds what we call the threshold energy value, then what we'll have, party people, is we will have an electron. That threshold, okay, let's make it green here, is right here. What I mean by that is if the energy of the photon, which is measured by essentially the frequency being high enough, all right, so if we have a high enough frequency, which is a very small wavelength, okay, that energy will be enough to not only remove the electron binding energy, give it some kinetic energy. So what did they give me in the formula, or what they give me in the problem, I should say? They gave me the maximum kinetic energy of the ejected electrons. So they gave me this value right here. So let's go find that. That value is 2.0 times 10 to the negative 19. Small amount because this is really per electron here, joules of energy. That's the kinetic energy. So that's the extra energy beyond the threshold. And so they want what? Well, they want calculate the frequency of light, okay, from this photon and the binding energy. So I'm going to go for the binding energy, which would be the difference between the energy of the photon. Well, the energy of the photon, they already told me was this right here was a 6.0, tough to write on the side, but I'll do the best I can. 10 to the what? Well, 10 to the negative 19. All right, so that's what this right here is. So this is basically going to subtract. So all I got to do is go 6.0 times 10 to the negative 19. That's what this arrow right here represents, the energy of the photon. It exceeded the threshold, so it was enough to give the electron some energy. And basically, I'm going to subtract that from 2.0 times 10 to the negative 19, and these are both joules. And you notice we're both in the same exponent, so this is pretty simple math. Okay, this is going to be 4.0 times 10 to the negative 19 joules, and that is what this value here represents. So right here is our binding energy, and that's what we have here. So that is equal to our binding energy. Okay, that's a really important part. That's what Einstein really postulated, is that energy, of course, or light travels in packets of energy called photons. They act like particles. They eject the electrons if they have enough energy per packet or per photon, per particle of light. Kind of weird. Okay, light matter duality there. Will remove electron. So if I know the kinetic energy, which is the excess energy beyond the threshold, all right, I know what the binding energy it takes to remove the electron. All right, now a couple of things they wanted. The binding energy in joules per electron, that's what this is. This is joules per electron, because this energy that we get per photon, or this energy they give you, okay, is basically made through this formula. All right, so this is already per electron. Now convert this to kilojoules per mole. Well, that's not a big deal. If I'm going to convert this to kilojoules, I'll take my 4.0 times 10 to the negative 19. And of course, that's joules. And what I'm going to do is I'm going to get rid of, all right, heck, drawing kind of small there. I'm going to just kind of get that there out of the way. And we'll just get rid of joules, so joules go on the bottom. And what do you want? Kilojoules. All right, so kilojoules a bigger unit, you get less of them. Smaller unit, more of them. They differ by 1,000. So I'm dividing by 1,000 there. Joules go bye-bye. And because they want it per mole, remember this was joule per electron, because that's how this formula works. It's per photon. And if you haven't picked this up, a photon, generally speaking, a photon, a packet of light that's basically measured by the energy of the frequency of that packet or light, okay, interacts with one electron. So this is the energy per one electron already. We want a mole of electrons, right? So this is one electron, and so what we're going to do, we're going to get rid of the electron here, right? And there's what? Well, there's an electron. What we know is that 1 mole is equal to what? 6.02 times 10 to the 23. Okay, and so I'm going to multiply that because I have by a single electron, right? So I want a mole of them, and I have to times it by Avogadro's number. And you notice electrons would cancel, and I get left with kilojoules per mole. So I'm going to take my 4.00 times it by 10, 4.00 times 10 negative 19, okay, divide by 1,000 times Avogadro's number, put that in my calculator, and I get approximately 241 kilojoules per mole. All right, mole of what? Well, mole of these photons, which will interact with a mole of electrons. Okay, and that's that part right there. Okay, now they did also say, please find the frequency of the light. Okay, and so like we just see, like we know, the energy per photon is equal per particle of light, Planck's constant times frequency. Planck's constant is given to you in your reference table, and this formula is given to you in your reference table. I know the energy of the photon is 6.0 times 10 to the negative 19 joules. I know Planck's constant is 6.63 times 10 to the negative 34, very tiny. Remember, he thought that that would just go to 0, but it actually is some integer. Okay, it's a joule second, and it's times by the frequency. So if I solve for the frequency, because they're asking for the frequency of light, what do I get? Well, do my algebra, and I guess I like writing all these numbers out. 6.0 times 10 negative 19 joules over Planck's constant, 6.63, another constant given to you in your reference table, times 10. Remember that he used that constant to figure out or satisfy the ultraviolet catastrophe. And therefore, he found that, well, he didn't find anything. He just fixed it. And other people interpreted Einstein that the matter is quantized. And in terms of Einstein, all right, he said it was the light that was the, basically was after the light was sort of had specific energy levels. All right, any case, that affected the electrons of matter. So it was the interaction. But in any case, negative 34, and these are joules seconds. And we can round off, or we can, I'm sorry, cancel. I'm talking about gymnastics all of a sudden. And notice we're left with a unit is equal to 1 over second, which is a hertz, or a cycle per second, which is a unit. 1 over second is a frequency per second. How much per second? So we put this in our calculator, 6.00 times 10 negative 19, joules over 6.63 times 10 negative 34 joule seconds. And what we get approximately is 9.05. And that's times 10 to the 14. It's a lot of cycles per second. Okay, and we could certainly go on our spectrum, okay, our electromagnetic spectrum, to see what kind of electromagnetic energy we have there. All right, and my guess would be in the visible spectrum somewhere. Any case, that is the frequency, and those are our answers to that question. Pretty straightforward. I mean, really, nothing crazy. the interpretation of what all this means is what was the major part of Einstein's Nobel Prize for interpreting the photoelectric effect. So let's go on to the next question. So number 6, the binding energy of electron of chromium metal is, okay. So that we know that's part of the energy of a photon if it exceeds these threshold to remove electrons. So this is the binding energy. And we're saying that's equal to, they're telling us 7.21 times 10 to the negative 19 joules. All right, so the first part, calculate the longest wavelength of light that will eject electrons. Kind of a weird way they're saying, but think about that. What's wavelength? Wavelength measures the distance of what? Of the start of the wave to the start of the next wave. It's that distance in meters. Okay, and we know that if the waves are shorter, you have a lot of frequent waves, the frequency's higher. So we know that a long wavelength, which means you're going to have a what? The longer the wavelength. What do we know, party people? Come on, think about this. Speed of light is broken up into the wavelength times the frequency. So if you got a long wavelength, you're going to have a what? Short frequency. So by me asking, or the question asking, calculate the longest wavelength of light that will eject electrons, what you're really saying is, what is the shortest frequency needed? And what do we know about frequency? Frequency times Planck's constant equals energy. So by saying the longest wavelength, because of this inverse relationship equal to a constant, all right? So we're really saying, hey, what is the shortest frequency needed to move it? And we know that, all right, having a lower frequency means you have the lowest energy. So what they're saying really is, what's the minimum amount of energy or the minimum amount of frequency, hey, okay, needed to remove that? Well, the minimum amount of energy needed to remove, okay, electron would be exactly a photon, okay, E of the photon, that actually equals the binding energy. So to find that what? Okay, the longest frequency, or the longest wave, I'm sorry, to find the longest wavelength, okay, I gotta find, I know that this has to be equal to my this has to be equal to my photon. So my photon would have to be exactly this binding energy. So energy is equal to what? Planck's constant times the frequency. What do I have here? Well, this is really the energy. Okay, and with Planck's constant, I could solve for frequency. Now, there's something else I can do here. I can combine these two formulas. C is equal to wavelength lambda times what? Frequency. Okay, since I'm really trying to find lambda, okay, let's solve for frequency. Okay, this one right here. So let's do this. So, and this is what you could do to make life a little easier, I think, or you can just do it in 2 steps. It doesn't matter to me. But V is going to equal to what? Speed of light over lambda. I'm just doing algebra, solving for V. So I know that. Now, why am I doing that? Because if frequency equals speed of light over lambda, and I have frequency here, I can what? Just substitute that in. And when I do that, let's change some colors here to get some contrast, I get energy is equal to Planck's constant times what? C over lambda. And what am I looking to solve for? The longest wavelength, or the wavelength in this case that is equal to that energy. Now let's just rearrange the equation one more time. What do we get? Lambda is equal to hc over the energy. Hey, okay, that's kind of fun. So you could have done what? Solve for frequency by plugging in the what? Planck's constant. This is the energy because it's going to match the binding energy to be the minimum amount of energy or the longest wavelength. Okay, and solve for this. Plug this into this formula. Knowing the speed of light's another constant you know. All right, you can solve for this, but I just kind of did it this way because I'm tall. All right, so let's plug it in. Planck's constant, okay, is equal to what? 6.63 times 10, and I don't have the room to do this, so I'll do it down here. So 6.63 times 10 to the negative 34. The unit is joules seconds. That's my H. Speed of light I know is 3.0 times 10 to the 8, and its speed is a meter distance per second. And I'm going to divide by the energy, which will be in joules, and that, of course, is the energy that exactly matched the binding energy. So the energy of the photon exactly matched that. So that's going to be 7.21 times 10, and I couldn't see that. My short-term memory's gone at this height, times 10 to the negative 19, and that's joules. Notice when we cancel our hearts away, we get joules go bye-bye. All right, seconds go bye-bye, and you're left with what? Meter, the distance from the start of a wave to a new one. So you put this in your calculator, okay? And what do you get? Lambda, the distance of the wavelength, is approximately equal to 2.76 times 10 to the negative 7 meters. Okay? Again, you could have done it in 2 steps or do what I just did there. All right? And then what they want is the second part, B, the frequency required to give electrons the kinetic energy of 2.6. So they want the frequency of what? The frequency of the particle of light, the photon, that would give electrons this kinetic energy. Okay, all right, the binding energy is that. So if we're looking for some kinetic energy, that's 2.5 times 10 to the negative 19. They're looking for the frequency. What would be the photon now? This E, the photon, is going to be bigger. So we've got to draw it bigger. It's going to go past the what? Let's make it red. It's going to go past, I didn't make it red, but hey, it's going to go past the threshold and equal this amount. So the new E of the photon, party people, okay, is going to be the sum of these two. So when you add 2.5 times 10 negative 19 joules to 7.21 times 10 negative 19 joules, okay, you get 9.71 times 10 to the negative 19 joules, and that's the energy of the photon. That would be enough energy to kick out the electron and give it this kinetic energy, okay? So with that energy, okay, knowing what? Energy is equal to what? Energy is equal to Planck's constant times the frequency. We have this energy. We have Planck's constant, and we solve for the frequency. Okay, so when you plug them in, I don't think I need to set that up anymore, but so you're going to plug that new energy per photon in with Planck's constant. When you solve for V, okay, algebraically, okay, I get energy per photon, which is the new value here, which is the sum of these two, over Planck's constant. And so when you do that, you should get 1.46 times 10 to the 15, and you will get 1 over second. Okay, and why does that work? Because I'm using joules, and Planck's constant is joules second. You notice the joules will cancel 1 over second. Okay, and that would be the frequency. And if you want the wavelength, okay, well, guess what? If I have now the frequency, and using my equations, okay, C is equal to lambda times the frequency. Well, solve for, what was it? My short-term memory's gone at this height. They want the wavelength. So solve for lambda. Lambda is equal to, algebraically, speed of light over the frequency. And just plug that in. You have 3 times 10 to the 8 meters per second over the new frequency that we just found to be 1.46 times 10 to the what? 15, and that is 1 over second. Notice what happens, party people. The seconds go bye-bye. Okay, and I'm left with meters. So when you plug that into your calculator, you get 2.5. So this so lambda equals 2.505, hey, times 10 to the negative 7 is going to be small. meters. And that's just it. So not a big deal. All right, hope that helped.